Okay, we're going to proceed with part 3 of the homework assignment solutions for week 3, which is now focusing on projectile motion. And basically, I want to point out the key to working problems with projectile motion is to divide any particular vector into its x and y components. There are some other tricks which we will point out as we go along, but that is a very important key as you move along. So let's take a look at number 29. An archer shoots an arrow at a 75-meter distant target. The bullseye of the target is at the same height as the release of the arrow. At what angle must the arrow be released in order to hit the bullseye if the initial velocity is 35 meters per second? 35.0 meters per second. Now, the easiest way to do this problem is to use the range formula, which is in the end of the chapter. And I would suggest, by the way, that you put this formula in your card of formulas that you're going to use. The range is equal to the initial velocity squared times the sine of 2 times the angle of release divided by g. Now, if we solve this, now what we want to know is this angle right here. So if we solve this, we get sine of 2 theta is equal to rg divided by v0 squared. And then working along, that means that 2 theta, or theta, is going to equal to 1/2, that's dividing by 2, the sine minus 1 of rg over v0 squared. So if we put this in, 1/2 sine minus 1, that's the inverse sine. The distance is 75.0 meters. We have 9.8 is g, and v0 was 35, and we're going to square that. And if we do this calculation, we get an angle of 18, I think it is, yes, 18.4 degrees. So that's part 1. Part 2 asks the question, there's a large branch halfway between the archer and the target, so that would be at the point of the maximum height of the arrow. And it wants to know, the branch is 3.5 meters above the release point. It wants to know what the height of the arrow is at that release point, or at that point, because it wants to know whether it goes above the branch or below the branch. Well, in order to do this section, you have to know that Vy at this halfway point is going to equal 0. And this also occurs at 1/2 the distance. Now, in order for you to see this, I'm going to draw a diagram. Here's the release point. Here's the target, and it goes up and back down, okay? So the halfway point is the highest point. It's also the point at which the y component of the velocity is 0. So we go from here to there and then back down. So that means that Vy is going to equal to Vy0, the initial y component, times the sine, Vy0, excuse me, not sine, Vy0 times or plus 1 gt, minus gt, sorry. Minus because the gravity is pulling it down. It's actually plus, but I'll just use that. So that means that t, so the time point where it reaches this point is going to equal Vy0 divided by g. And Vy0 is V0 sine of the angle, which we got here, divided by g. So that means it's going to be 35 times the sine of 18 degrees, 18.4 degrees, divided by 9.8. If you do the math here, you get 1.13 seconds. And then the distance, y, is equal to vy0 t minus 1/2 gt squared. And if you put the numbers in, it's going to be 35 times sine 18.4 times 1.13 minus 1/2 times 9.8 times 1.13 squared. And if you do the calculation, crank this out, you get 6.14 meters, which is well over the 3.5 meters. So it goes above the branch. The next problem is problem number 33. Problem number 33 states, a cannon on a battleship has a shell of a maximum distance of 32 kilometers. So R is equal to 32.0 kilometers. Now it says maximum, so that means the angle has to be 45 degrees. And you can look in your book, in the projectile motion, you can see where I got this. But whenever it says the maximum distance of a particular object, it has to be shot at 35 degrees. So it says calculate the initial velocity. Well, the initial velocity, we're going to use our range calculation again. So R is equal to V0 squared sine 2 theta over G. So that means that V0 squared is equal to RG divided by the sine of 2 theta. And so if we take that square out and just make this a square root, that should give us the answer. This is 32 kilometers. This is 9.8 divided by the sine of 2 times 45 degrees, which is 90 degrees. The sine of 90 degrees is 1, so you end up with the square root of 32 times 9.8. Now, in order to do this rightly, you should change this to meters. So this is 32,000 meters times 9.8. So V0 is 560 meters per second. And you could put this down as 0.56 kilometers per second if you wanted to, and it would be okay. Now, another problem in your book that you might want to write on your card is the height of any object is equal to V0y squared over 2 times g. And this will answer the second question, which is how high does the projectile reach? Well, if we put in remember V0 is this, so V0y is V0 sine of theta divided by 2g. So that's going to equal 560 times the sine of 45 degrees, and that quantity squared, divided by 219.8, 2 times 9.8, 2 times 9.8, and if you do the math here, you get 8.00 times 10 to the third meters is its maximum range. Now part C, I'm not going to talk a whole lot about part C because it's a little bit complicated, and I wouldn't put a problem like this on a quiz or test. But part C asks how far above the surface of the water will this go? And probably the best way to look at this, first of all, you have, this is the radius of the Earth, this is x, which is the distance from where the shell goes. If the shell's fired from here, it goes from here to here, and this is the angle alpha. Now, this little arc here is the arc of the Earth that's subtended by alpha. Now, in order to find out what alpha is, you have to take the 32.0 kilometers and divide that by the radius of the Earth, which was given in the problem, and then to realize that that times pi times r is the total circumference of the Earth. And this represents that arc, and if you want to represent that as an angle, you multiply that, realizing that circumference is 360 degrees. So the total is 360 degrees, and this is the fraction of the total that we're talking about. And so if you do that, you get an alpha of 0.2878 degrees. Now if you take that and realize that this line radius r is equal to x times cosine of alpha, that means that x is going to equal to r divided by the cosine of alpha. And if you take the cosine of 0.2878 and divide that into the radius, you get 6.37008 times 10 to the third. So the difference here is 0.00008 kilometers. 0.00008 kilometers. And so that's going to be, if we look at that, that's going to end up being times 10 to the 8th, times 10 to the third. So you take the 10 to the third out, and that moves the decimal 3 places. You change that to meters, that changes this into 80 meters. So it is 80 meters above the surface of the water. The next problem we're going to do is number 38. Number 38, and remember number 38 because another problem we're going to end up doing comes back to number 38. Number 38 talks about a quarterback who is running backwards at a speed of 2 meters per second when he releases the ball. And he releases the ball, and it ends up going 18 meters to a guy downfield. Now, it says that he catches, the angle here is 25 degrees, and the receiver catches the ball at the same height that it was released. So we use our range calculation again. This range calculation is equal to the initial velocity squared times the sine of 2 times the angle of release divided by gravity. And the question is, what is the initial velocity? So what is V0? So we have RG, moving g to this side, and divide that by the sine of 2 theta, and take the square root of that, and that's going to give us V0. So that's going to be the square root of, and we throw in an 18 meters downfield times 9.8 divided by the sine of 2 times 25 degrees. And if we do the math here, we end up with 15.2 meters per second. So that's A. B states, asks what the flight time is. And the easiest way to do the flight time is to realize that the horizontal distance is equal to the x component of the initial velocity times the time, because there's nothing acting on that x component to slow it down. So that means that the time is going to equal the x distance divided by the x component of the initial velocity. So this is 18 over 15.2 times, and the x component is the cosine of 25 degrees. And if we do that, we end up with 1.3 seconds as the flight time. Now part C asks the height of the ball. What is the maximum height? And again, we use that height formula, which says that the height is equal to the y component of the initial velocity over 2g. And so that's going to be the initial velocity times the sine of the angle of release over the 2g, this squared. So this is going to be 15.2 sine 25 degrees divided by 2 times 9.8. We do the math here, and you get 2.11 meters above the angle point of release and the point of where the person catches it.